Hi everyone, this is my video number 12. Right, so if you still remember in my last video, I asked you to show that this sequence is bounded. Oh, -1. This is un -1. So I've shown asked you to show that this sequence is bounded. First thing, look at that sequence. If you can recognize this, so let's see this. You see, u1 is 0. If you try u2 is what you have 2 plus u1, right? So we have this is 2 plus 0, that's square root 2. Okay, square root 2, this is definitely less than 2, right? If you find u3 is 2 plus u2, that give a 2 plus square root of square root 2. And you can proceed this. If you find we can find u4, for example. So we have u plus u3, so that give you square root of 2 plus square root of 2 plus square root of 2. And you can continue this up to un and so on. Now we want to show this. I think the best approach is using mathematical induction. I think you know what is mathematical induction. Mathematical induction. What is mathematical induction? First thing is that we know u1 is true. U1 is, this is 0. This 0 is definitely less than some numbers. Alright, let's say those number, look at here, it seems this is less than 2, so let's say this is less than 2, so this is true. Okay, and then we assume that it is true for n equal to n, which means by observation we can see that un less than 2. So we assume this is true. Why less than 2? Because you can see here, this is square root 2. This is obvious here. Square root 2 is less than 2. Here is less than 2. Definitely here less than 2. So everything is less than 2. Okay. Now we assume that assume it is true for un, and then we need to show it is true for n equal to n plus 1. If you can show it's true for n equal to n plus 1, so it means it's true for all cases. Yeah, so for n equal to n plus 1, so what we have, un plus 1, this is square root of 2 plus un. Okay, if you take the absolute of that un plus 1, you take absolute of this. Alright, so what you can write here, this is square root of, you can write this in terms of that. Alright, and use appropriate inequality here. So this is less than 2 to the half plus un to the half. Alright, and then you can use triangle inequality. This is definitely less than 2 to the half plus un to the half. This is square root 2. This is less than 2. Alright, so we have this is less than 2 definitely. That you can we have shown up there, this is less than 2, so this is less than 2, so all total this is 4. So then you can show that the un, basically this is your m. So therefore your un defined by those un is bounded. Remember that when we talk about boundedness of the sequence, we need to find a certain number that our sequence will not exceed those number. Okay. Now, in the exercise, there are many in the notes that you can download from Putra Blast. There are many exercise activity you can do. For example, I just show one of these. You have sine n pi over 2, that sequence. Okay, this also obvious that it's less than 1 because sine cannot be greater than 1. N pi over 2, this is less than 1, so this is bounded. So this sequence where your un is this, your un is bounded. Okay, right, so I think I stop there for the boundedness. Now let's see how can we find the general formula for the sequence. General formula for this sequence, for a sequence. What do we mean by general formula? For example, if I have sequence, let's say I have 2, 3, 5 and so on. We need to find un. What is un? This means by general formula, we need to find un. So this is by inspection. We don't have a specific rule for this, but you can, of course, you can by looking at the pattern of those sequence, you can find what un is. So here in this case, we have 1, 3, 5. This is all odd numbers, begin with 1. All right. So you can find this. Then you can easily find that un is equal to n minus 1. In fact, if you still remember the arithmetic series and another one is arithmetic and geometric series. All right, that I think you have learned this thing only in the school. So there is a formula to find the n terms of those sequence. Now, let's try with other example. What if you have other example? If you have, let's say, this sequence, 1 over 5, 1 over 7, 1 over 9, and so on, and un, and so on. So we need to find the n terms, un. Okay, if you look at here, this is 5, 7, this is all odd numbers, and this begin with 5, not begin with 1. So definitely you know that from there, it must be kind of 2n minus some odd numbers, or un plus some odd numbers. This is u1. Right, that's u1. So for u1, this is u2, u3, and so on. So for un, you can see the thing that the numerator doesn't change, 1 everywhere, 1. So you can write that's 1 over. Okay, that's 1 over. Then down there you have 2, 7, 9, and so on. All right. So it's an odd number. So odd number you need to n, either minus or plus. If you put minus, see what happened. Minus 1, for example. If you put minus 1, so when n equal to 1, you got 1. So definitely this is wrong. So if you put minus 3, getting smaller, so it should be plus. So if you put plus 1, so when n equal to 1, you got 3, but here is 5, still not correct. So I think 3 should be correct. Okay, n plus 1, when n equal to 1, 2 plus 3, you got 5. When n equal to 2, 2 times 2, 4, 4 plus 3, 7, so you got 7. 6 plus 3, 6, 9, so you got 9, and so on and so forth. So this is true. So that's the way we do we find the n terms of the sequence. Okay, other example, if you have this sequence 4, 7, 10, and so on, un. Okay, this is first term, un, your first term. The difference is 3. You can see this is 3, this is 3. This is a arithmetic series. Yeah, arithmetic series. Your first term is a. That's your a is 1. Your what we call that the difference is 3, so that's d is 3. So you can find un is a plus n minus 1d. So your a is 1 plus your n minus 1. Right, so we have n minus 1. Your d is 3. So if you solve this, you got 3n minus 2. Okay, you can do the same here. Just simple example here. You can do the first term here is 1. The difference is 2 everywhere. So you can find un is, can use that formula, a plus n minus 1 d. So we have 1 plus your n is n minus 1 d is 2. So we have 2n minus 1. See, it's just the same in that. I think you can do this as well. Just consider the denominator where you have 5, 7. You can try that. 5, 7, 9, and so on. Alright, so the first term is 5. So you have un is equal to 5 plus n minus 1. The difference is 2. So we have 2n plus 3. See? The numerator. Okay. Let's see other example. Let's see a few other example. If you have let's say 1, 3, 9, 27, 81, and so on, un, and so on. Okay, we need to find un. If you look at this, okay, you can divide this to un plus 1 over un. If you divide this, what you have? 3 over 2, 3 over 1 is 3, 9, 3, 27, 3, and so on 3. So this is 3. You give name is, this is your r. Okay, your first term is 1. First term is 1 here. A. So to find un, I think you have a formula for this. That a rn minus 1. Alright, that give you, so your a is 1, your r is 3, then n minus 1. Then you can check. Now you can check. When n equal to 1, you got 0, 3 to 0, 1. When n equal to 2, 2 minus 1, 1. 3 to the power 1, 3. When 3, and so on. So you remember that this un 2, 3. So it's, but this is u1, u2, u3, right, and so on. Remember this. Okay, you have to look into those subscript. All right, what if you have a sequence like this? Okay, another example. I give you many examples here. That we have 1 over sec 2, 1 over sec 4, 1 over sec 4, 1 over sec 8, 1 over sec 8, and so on. Un. You need to find un. So look at this carefully. So we have u1 here, u1, u2, u3, u4, u5, u6, and so on up to un. Okay, look at the where the terms start to change. Okay, here 1 over sec 2, then same value, 1 over sec 4, same value. So it's jump 1 terms. Okay, it's like it's jump 1 terms. So look at this, that, and you can expect next is u7. So u1, u3, u5, next is u7. So, and also if you look at the second term is the same. Next term start change is term number 4, and then term number 6, and so on. So by looking at that, you can see here, this is for un, this is 1, 3, 5. So you have an odd number. So you have 2n minus 1. 2n minus 1, this is 1 over, everything we said, we have 1 over, you have square root 2, 4, 8, and so on. So we have 2n. That for n equal to, this is for n equal to, let me write here, for n equal to 1, 3, you got 3, 6, 6 minus 1, 5. So u5, that, is that correct? No, 2, 4, u3, no. For n equal to 1, 2, 3, okay. Let's go. For n equal to 1, 2, 3, and so on. Okay, but by doing this, basically we are not including the odd terms, the even terms. So for the even terms, so we have, look at here, we have 2, 4, 6. So we have 2 un, this is equal to just the same, right? So square root 2 over n. So that's your n terms. 2n minus 1 terms, and 2n terms. So just looking by looking at the pattern of each term, then we can determine the general formula for that. If okay, one more example. We have many examples here, but I think we have many examples. It should be one more. Okay. Another example. Let's say if you have minus 1, 1 over 4, minus 1 over 9, 1 over 16, minus 1 over 25, and so on, 1 over 36, and so on. You need to find un. Okay, so by looking at these numbers, these terms, you can see this is basically 2, 2, 2. This is 3 squared, this is 4 squared, this is 5 squared, this is 6 squared. Alright, u1, u2, u3, u4, u5, u6. Now you can see for u1, 1, definitely this is u1 squared, because this is 1 over 1. Alright, so look at the denominator. Numerator doesn't change, so we don't have to worry about that. But look at the denominator. So we have 1 squared. This is u2, we have 2 squared, u3, 3 squared, u4, 4 squared, u5, 5 squared, u6, 6 squared, u7, 7 squared, and so on. Alright, what difference is that? You have a negative, positive here. Negative, positive, negative, positive. First term is negative, second terms. The even terms, positive, odd terms, negative. So this is easy. So therefore you have un equal to, we have surely minus 1 because it's alternate, negative, positive, negative, positive. The first term is, so we need to make it to the power of something that make second terms second term negative, second term positive, third term negative. So I think this is obvious. 1, 2, 3. So I think that's, you can put n. When n equal to 1, negative 1 to power 1, you got negative 1. So when n equal to 2, negative 2 to power 2, so you got positive. 3 negative, 4 positive, and so on. Alright. Then inside there, this is 1 over, for the numerators, this is 1 over 2, 3. So we have n squared. Okay, write it properly. So we have minus 1 n over n squared. That's your un. Okay, now one more. I think I need bigger space. Let's say we have 1 minus 1, 2 minus 2, 3 minus 3, and so on. We need to find un. Same approach. This is your u1, u2, u3, u4, u5, u6, u7, u8, u9, and so on. So u1 to u4, u4 to u7, u7 you should expect next is u10. Okay, u2 goes to u5, goes to u8, and you should expect next is u11. Yeah, u1, u4, they start changing from 1 to 2. u4, u7, 2 to 3. The rest is the same. You can see the same there as well. So in this case, you see one. Look at the subscript of u here. u1, u4, u7. So what you have here? So you have u. I think we have evaluated this. I think 2n minus 1. When n, yeah, 3n minus 2, right? This is 3n minus 2. So when n equal to 1, so we have u1. When n equal to 2, 6, you have u4 there. When n equal to 3, you got 9 minus 2, 7, so you got 7, and so that's correct. Alright, next is 2, 5, 8, and so on. So that's u 3n minus 1, right? When n equal to 1, you got u2. N equal to 2, you got u5, and so on. Yeah, that's correct. And then next is u3. So u3, u6, u9. So u3n. Okay, what is this? You need to find this. So here, when n equal to 1, you got 1. When n equal to 2, 2. When n equal to 3, 3. So basically, number of terms equal to that. So this is n. This is n. What about u3? u3, this is minus everything, but still 1, 2, 3, 4, 5. So this is minus n. So that's your n terms. Easy, right? That's your n terms. I think you can find more in the any sequence book, in the book, calculus book, look at the particular chapter sequence. You have many other example exercises. All right. Let's say another one. If you have terms like 1, 1, 2, 3, 5, 8, 13, and so on. UN. What is UN? Look at this is U1, this is U2, this is U3, and so on. If you look at this carefully, for U1, U2, the same value here, but U3 is, we add up these two terms, we got that. U4, we add up the previous two terms, we got 3. U5, 3, 4, 5, U5, we add up the first two terms. So it is obvious from here that UN is equal to UN. You can take UN plus 1 or UN is equal to UN minus 1 plus UN minus 2. You can do this, but your n must begin from 3, because you cannot have, when if n begin from 1, you got n minus 2, you don't have u minus 2. You don't have u minus 2. So make sure the first term here is u1. So you put 3 minus 2 is 1, so you got u1 there. Okay. Or you can also have un plus 1. This is just un plus un minus 1, just the same thing. But in this case, n begin from 2, and so on. Okay, so this we call it as a Fibonacci sequence. Fibonacci sequence. If you want to know who's Fibonacci, is a Italian mathematician. You can check in internet, search, then you can find whose Fibonacci is. Okay, I think I will stop there. We also have Lucas sequence. Right? How to spell Lucas? Lucas CS. Lucas sequence, given as 1, 3, 4, 7, 11, 18, and so on. UN. You can find UN there, right? Look at this U1, U2, U3. Alright, so what we have here, you add up these two, you got that. For that, you add up these two, you got that, and so on. Alright, again, UN is equal to UN minus 1 plus UN minus 2. For n, 2, 3, 4, 5, and so on. Okay, so I stop there for the general formula for the n terms of the sequence. Right? Thank you.